Today I'm going to show you a new and very interesting way to quantify shape. How does one describe a shape using numbers? There's a whole bunch of different things that we could measure about a shape, like the ratio of the height to width, the ratio of the perimeter to the area. You can even measure like the roundness. But even if I gave you all of these properties, it doesn't really tell you the essence of the shape and certainly not what the shape looks like. So there's something missing. In 3D computer graphics, you can describe shape using something called a polygon mesh. And that's where you go and store literally every single polygon on the surface of this shape. This has the advantage of being a really precise description of shape, but it takes up a lot of data and it's just not a very holistic way of describing shape because you're just listing every little piece that comprises it. What if we could find a more compact representation of shape, like a feature vector?
Data.
I found this paper that uses a machine learning model based on point net. This is a type of network that operates on point clouds as input. This model is not only able to understand the shape of the point cloud, but it's able to form a descriptor vector for that point cloud. Using this model, we can create these shape descriptor vectors corresponding to each letter of the alphabet. I'm going to start by giving a high-level analogy of how this model works, and then I'll go into more details about how the actual point net model is set up. Let's say we have this data set of 10,000 cookie recipes. Each cookie recipe is defined by these four numbers, which is how much flour, eggs, butter, and sugar that it has in grams. And we have these two devils with different dietary preferences that are going to corrupt these recipes based on their dietary preferences. We're going to cycle through this entire data set and compare the original recipe to the corrupted recipe. And what we want to do is we're trying to infer something about the dietary preferences of each devil. And the preferences is defined in terms of how much carbs, protein, fat, and sugar that devil eats on average. When the experiment starts, they don't know anything about the dietary preferences. And we start noticing this pattern, which is that devil A, his recipes come out with way lower sugar than the original. Devil B, his recipes come out with way lower eggs and butter than the original. So over time, we start to say, okay, devil A, we're going to call him the keto devil. We're going to reduce his sugar and his preferences. And the other one we're going to call the vegan devil. We're going to reduce his protein and fat. So what I'm trying to show here is that by looking at how the original becomes corrupted, you can start to infer something about the entity that's doing the corruption. In the real model, this diet preferences vector is analogous to the shape descriptor vector. This shape descriptor vector is encoding something about the shape of the point cloud. Here's how the actual point net model works. This model is based on a class of models called point nets, which operate on point clouds as their input data. And a point cloud can be defined just as an array or a list of points in 2D or 3D or however many dimensions. We can have this point cloud and we can add noise to each point. So we can add a little jiggle to every single point and produce a noised point cloud. And that has the effect of kind of blurring the point cloud. And you're losing some information about the shape here, right? This is foreshadowing for later, but the more noise you add to the point cloud, the more you lose information about its overall shape. What happens at each iteration is that you take a point in this point cloud and you add a little bit of noise to it. You corrupt it, and you then take that noise point and you concatenate it to the shape descriptor vector for that point cloud. Both these pieces of information go into the model, and the model's role in this is to predict the original uncorrupted point, the denoised point. And so the model is kind of in charge of reconstructing the original point cloud. What we're really after here is not a model that can reconstruct a point cloud. What we really want is the shape descriptor vector for the point cloud. So what happens more concretely in this model is that one point cloud is one training instance. The blue model there is like a multi-layer perceptron that's shared among all points. And the shape descriptor is also shared among all points. So it's just repeated and concatenated to every single point. Each one of those vectors goes through the model. The model outputs the denoised point, and then we can compare it to the ground truth using a loss function. I'm simplifying a bit, but the loss function is basically just the mean squared error between the ground truth point cloud and the denoised points. This provides us with a signal that's used to optimize this model, and we are also learning the shape descriptor itself. To learn, in machine learning means like to build, to construct it iteratively means to learn. The shape descriptor is this vector that starts off and we don't know what it is when we start out, but we're going to try to learn it. These are actually learnable parameters in this system. What's going on here is that we're asking this model to predict the original point cloud using a corrupted piece of information, which is the noised point cloud. But you're giving it the option to have this additional piece of information to help out. When we noise the point cloud, we're removing information about the overall shape because the shape becomes blurry. So that missing information has to come from somewhere. In setting up the model this way, we are encouraging the information that was lost in the noising process to become infused into the shape descriptor vector. It's genius. To test this model, I created this database consisting of point clouds in the shape of letters at various rotations. We're rotating them in order to do data augmentation. After the model was done training, I found it does a decent job of reconstructing the original point. So in order to test whether this worked, I took my learned shape descriptors and embedded them into 3D using dimensionality reduction. And when you embed that into 3D, you find that indeed you get approximately these 26 distinct clusters. We indeed found that each cluster corresponds to a single letter. It's not perfect, but I think that's pretty definitive that this worked and this actually created a vector that described the shape. I hope you got something out of that. This project will be on GitHub. Thanks so much for watching. I'll see you next time. Peace out.